resume the recording. And let me share my screen so you can see how to access the materials if you want to follow along. If you just want to follow along and listen and not do any coding for the second part, that's totally fine too. If you're here just to get a sense of like, oh, what are some other ways you can approach network analysis, and what are some other things that network analysts often look at when they're looking at social networks, which is totally fine. Like I said, if you don't feel like booting up RStudio Cloud and getting everything and yanking it down from GitHub, I already have everything set up for you in RStudio Cloud. RStudio Cloud, if you're not familiar with it, it is just like RStudio Desktop, except instead of it being an app based on your desktop, you just do it in the cloud. It's almost the same features and functionality of desktop, but in the cloud. There are some bugs. Some things when you knit documents like R documents, some things don't always render as you would expect them to. Also, because I am paying for this out of Laser Institute funds, I have some of the settings set up for RStudio Cloud. I have the settings set up for like minimal CPU and RAM use. So things will run a little bit slower than they would on RStudio Desktop. The advantage of RStudio Desktop is it's rarely ever buggy, and it's going to run as fast as your computer runs, and it's going to have the full resources of your computer. But let me go ahead and just as a refresher, first of all, I'm going to share this link to this project for you. So I have lots of projects set up for Laser and for my classes and things like that. But I have a space set up just for us for these workshops. And I'm going to go ahead and copy the sharing link. I'm going to put this in the chat for you. And all you have to do is click on this link and you'll become a member. So let me put this in the chat. And there we go. It should be in the meeting chat now. And if you click on that link, it should take you to our space. And you can see I'm a content manager of RStudio Cloud, this workspace that we have. So I can see everybody's project, which is really nice because I don't know if you've started using R in your own teaching or in your own work, but when I'm working with students, I prefer to use RStudio Cloud because then their data analysis projects, I can access all of their R scripts and all of their files, and I can help them debug code, and I can see everything that they're doing. And then on top of that, they've added a new functionality to RStudio Cloud in that I can, just like a Google Doc now, when we're working on an R script, we can actually work on the R script in real time together, and they can code and type, and I can code and type, and I can see what they're doing, which is super nice. So something to consider if you're ever thinking about using RStudio in your own teaching. So when you log in, you should see something that looks like this: social network analysis and STEM ed. And it says assignment because I set it up as an assignment. And when you click on it, what it's going to do is basically copy this entire R project, and it's going to create a copy that's just yours. So we can see, Larissa, I see your project in here. So if you're ever having trouble, I can just click in on your project and I can see the code that you're typing and help you troubleshoot and things like that. So anyways, I'm going to go back in here. Like I said, you can follow along like in real time, but you don't have to if you don't want to. And if you want to follow along with the slides and pull them up too, there is in our Lab 3 folder, this is SNA Lab 3, there's a R Markdown file, RMD. R Markdown files, just to jog your memory from the summer, these are text documents that you can turn into a whole mess of things. You can turn them into slideshows, you can turn them into interactive web documents, you can turn them into dashboards, you can turn them into tough style handouts, a whole mess of things you can do with R Markdown, which is super nice. And this is what the code actually looks like for the slides that I'm about to share with you. And you can see it's a mix of text and it's a mix of R scripts too. And if you open up this file, SNA Labs 3 slides, there's a little yarn ball and you can knit this document and it's going to knit it and turn it into a presentation for you. And it may ask you to install some packages too, and just say yes to that. And these are the slides that we're going to be working with today. And what's nice too is I have it set up for, in my description of this file, I have it set up so every time I like restart this file and reknit it, it's going to update it with the most recent date too. All right, any questions so far? Or any assistance you need? Nope, okay, great. We are diving a little bit deeper into network analysis. So if you missed the first couple of labs, we did like in SNA Lab 1, a very simple overview to what network analysis is, some of the kind of core tenets of network analysis, its emphasis on visualization, its emphasis on relationships. In Lab 2, we took a look at some basic metrics for network analysis. That are often used in network analyses, like measures of centrality, for example, like how centralized the network is around one or two or a few individuals, which has implications for certain outcomes in education. And we also looked at things like density, like how dense a network is, how tightly connected people are in the network. And what we're going to do in Lab 3 is we're going to zoom in a little bit. So we've looked at measures of networks as a whole, like whether a network is very centralized or decentralized, whether a network is dense or not dense. And now we're actually going to take a look at ways we can identify groups within a network and put together measures for those networks, and then also measures for individuals in this network. So for example, in network analysis, one of the kind of core theoretical concepts is that where you are in a network, where you exist within the structure of this broader network, could potentially provide you with opportunities and access to resources or knowledge or information, or it could limit your ability or limit certain outcomes for you as well. And network analysts have devised a whole host of measures to describe mathematically like where you are in this broader structure of a network. So in the first part of the presentation, we're going to focus on like identifying groups. Like we're going to look at different approaches to examine like how we identify like whether communities or small groups are starting to emerge within these networks. Is anybody familiar with the word clique? Back in the 90s when I was in high school, this notion of cliques in high school was very prominent. And there was like sports cliques, and there was like the theater group clique, and then there was like a whole host of other cliques. But it's a formal term in network analysis, and we're going to look at different ways to identify cliques and groups and ways we describe and define those things. And there's a couple methods we're going to look at. We're going to look at top-down methods for identifying groups, and we're going to look at bottom-up methods too. And then we're going to look at a real example in the literature for this cool project called #CommonCore that looked at communities that developed and formed within this Twitter network focused on discussion around the Common Core state standards. And then in part 2, we're actually going to get some hands-on practice looking at groups and defining groups and also putting together measures for individuals within the network too. So that's the agenda for today. I'm going to pause after each slide, so I'm not talking the whole time, and pause for any questions or comments or anything before I move on.
I might be messing up some, but why is my agenda different than yours? Like the
one. Oh no, good question. When you have your documents, you're looking at your source pane. Does yours say SNA Lab 3 slides?
Oh, that's my mistake. All right, thank you.
Oh, yep.
Yeah. All right.
Are you on Lab 2 or Lab 1?
1. All right, makes sense. All right, I'll fix that. Yep.
Mike, totally fine though. You might want to keep those open just to kind of review and refresh too. Because
Okay.
Mike, I don't remember, were you here for lab 1 and lab 2 before?
I did one, I missed 2 though. So yeah.
Okay, yeah. I would definitely pull up lab 2 at some point and kind of review that, because that's where we introduce some of these basic measures.
Gotcha.
And when we get to the key actors, identifying who are these sort of key individuals in the network, there's a formal terms in network analysis called like popularity and popularity effects and degrees and things like that. We introduce a lot of that in lab 2. All right, so quick refresher. In previous labs, we covered data management, like how we go about collecting network data, how we store it in actual files, and differences between edge list for storing and capturing those relations between people, and matrices too as another way to store relations between people. And also, Mike, I just mentioned this in our last lab, we also introduced these concepts and ways to measure these concepts called centrality and density and reciprocity. This one here in particular, centrality, is really core to network analysis. And when you are like scanning the literature for looking at how other researchers have applied network analysis to contexts that you're interested in, there's probably like a 90% chance they're going to talk about measures of centrality, and they will be incorporating those into their study. And again, just as a quick recap, centrality is a way to, at the network level, to describe mathematically how much the network is centered on a few individuals in the network. And you can also have measures of centrality for individuals in the network as well, like whether there's someone connected to a lot of people, and whether the people that they're connected to are connected to a lot of people, or whether there's someone more isolated in the network and have very few connections in the network. And quick pop quiz, does anybody remember what reciprocity is in network analysis? Don't make me call on you.
Okay, so reciprocity is when you're actually like there's a tie between actor A and B that goes from A to B, but then actor B also has a tie that goes from B back to A, right?
Yep, you got it. And to make it a little bit more concrete, can you give an example of a reciprocated tie in a network?
Oh, so we did that study with those elementary school students, right? Or middle school students, and where the students are asked to identify who in the classroom was their friend.
Yep.
So if 2 people identified each other as a friend, then that would indicate reciprocity between those 2 students.
You got it. Yep. So that would be an example of a reciprocated tie. And another example might be like, we're going to be working with Twitter data. So it might be 2 people who reply to each other in a thread, or 2 people who follow each other. Or thinking of another example, let's see. Oh, so many examples. With our MOOC study that we did, we were looking at the degree to which our prompts resulted in people having discussions or dialogue. And part of a dialogue is back and forth discussions, right? Not just people piling on their thoughts, but no one actually responds to anybody else. So we looked at people within these discussion forums who actually replied to each other back and forth. What we actually didn't see was a lot of back and forth discussion. What was unexpected, though, is that even though there wasn't a lot of back and forth discussion, the way the discussion ended up evolving into pretty rich discussions as measured by Gao's online productive discussion framework, which was really interesting. But I won't get into that. That's for a different time. So that's just a quick refresher. A quick quote from our Carolyn book, which I highly recommend if you are thinking about incorporating network analysis into your own work. Carolyn wrote this great book called Social Network Analysis in Education. It's a little dated now. I think it's from 2014, but still super relevant. And one of the data sets that we use is from his book, and it's freely available to anybody. But he also has a lot of other data sets that are incorporated in that book too, and really good examples from the literature of network analysis being applied. But anyways, he said, unlike most social science, network analysts identify groups through their relational data, not through exogenous attributes such as grade level or departmental affiliation or years of experience. So it's not being a part of a group simply because you're in the same classroom or simply because you belong to the same race or ethnicity. The way we define groups in network analysis is because you have shared relationships among other members who also have similar shared relationships. So think of a classroom as like maybe a big group or a network context, but groups within that network might be like elementary kids who play together frequently on the playground, who are often in like reading groups or small instructional groups together. So anyways, it's a different way of thinking about belonging to a group. You belong to a group based on your relationship with other individuals and their relationships with other individuals, as opposed to some sort of trait that's placed upon the individuals. All right, so in part one, we're going to talk about ways to identify groups, top-down approaches, bottom-up approaches, and then we're going to look at an example from the literature from a really fun project called #Common Core. Okay, so top-down methods. We're going to talk about like a few common approaches, but these top-down methods are very, very simple definitions of group. But basically, top-down approaches focus on how larger network structures are built from smaller ones. This is actually from Carolyn's book, and he has a nice way of saying it. He says, this approach takes the complete network and considers parts of it that are dense and distinct from the rest of the group. And we're going to look at some examples of what that actually means. So one way to think of a group is to think about within this broader network. Melinda, if you remember, you had mentioned our middle school students from, I think it was SNA Lab 1. Our middle school group had, if I remember correctly, it was kind of two components in that group. Everybody was connected to everybody else in some way through some degrees of separation, except for that one isolated student who was an entirely separate component. But basically, a definition of a group, when we say component as a definition, it simply means that those individuals in this broader social network, those individuals are only connected to each other, but are separated from everybody else in the group. And what you're looking at here is actual data from an actual network study. And this was a collection of, I think it was teachers in a school district in California that were undergoing this big school reform as a result of being penalized during the No Child Left Behind era for low test scores. So they were undergoing these big school reforms, and these ties between teachers are teachers who said they collaborated with other teachers. So just looking at this and thinking about that definition of a component, which is basically sort of networks within a network that are isolated from other networks, roughly how many components are in this network? How many groups? And you can take like just a rough guess. You don't have to count them all. I counted about 13. Anybody else confirm? So there's 13 components, and that's like the simplest way of defining a group. So we clearly have this little component over here, the structure. If you can see my mouse, does everybody see my mouse? Okay. This is really interesting because this little group right here it's a very centralized subgroup, a very centralized little group right here, where everybody is saying they collaborate with this one person, but they don't collaborate with each other, which is fascinating. And I wonder what this actually represents within this particular school, or within this district, rather. Maybe this is a lead teacher, and these are, maybe it's an instructional coach. I don't know. But anyways, component is one way of defining a group. Another way of defining a group is by components. Melinda, we're getting back to our definition of reciprocity. But effectively, another way of defining a group is, we call these like weak, I'm sorry, gosh, I need to jog my memory. But it's weak components and strong components. And weak components are kind of just what we saw over here. But a way to whittle down the definition of a component and make it even more restrictive is to say, for strong components, we're only going to count the ties between individuals if they're reciprocated. So you could imagine if we're only looking at reciprocated ties between individuals, there's going to end up being even more components and more brokenness in this network and more individual kind of subgroups within this network, because ties often aren't reciprocated, especially in certain contexts like discussion forums or Twitter networks, or sadly, even friendship networks, where I think you're my friend, but Mike says, no, he's not my friend. And that's an example of like an unreciprocated tie. And then those strong components and weak components, it takes on a different shape of the network. But again, like, just keep in mind that these are just different ways of, my project went to sleep. These are just different ways of defining groups within a network. And then we'll eventually get to the point of, so what? Like, why does it even matter if we define groups?
And Sean, we're talking about directed networks here, correct?
Yes, but yes. Good question though, Melinda, because if we have something like an undirected network where either a tie exists or it doesn't, then there's no difference between a strong component and a weak component. All right, another way of defining a group from top-down methods are, and these are probably honestly the most common that you will see in network studies and network papers. One way of describing it's a faction, but it's basically a group with more ties within the individuals within that group than ties with other people in the network. And there's a whole host of different community detection algorithms for identifying and describing and defining these groups of tightly connected people. If you click on the link in the slideshow, one package that I often use for network analysis, which I really like, is a relatively new package called tidygraph, which basically takes the tidyverse approach to network analysis. But you can see within this, there are graph creation, community detection algorithms that are built into this, and different ways of describing groups. And this is just a small sampling of community detection algorithms. But back over here, I'm not sure which specific algorithm they used for their group detection, Melinda. And you can often restrict these two to say, hey, I'm only going to look for, let's pretend there's only 10 groups in this. Or let's say there's only going to be 5 groups. But this is kind of what their network graph looked out. And remember, this is, these algorithms come in handy when you're dealing with networks that are incredibly large. So this Twitter network was, I think, data that was collected over, gosh, I think maybe 5 years or even more than that, that consisted of like tens of thousands of Twitter users over time. But what they thought was really interesting, we'll actually go ahead and dig into it in a little bit, was like what these groups signified and why these people were grouped together as opposed to other people. Can you, I'm kind of curious, any guesses what some of these factions or groups in this Twitter network around the Common Core might represent, or how they came to be? And if you're a Twitter user, it might become like pretty apparent pretty quick.
Would there be people who weren't real happy with the Common Core?
Two of the main groups were proponents and opponents of the Common Core. And what you would often find too is that there wasn't a lot of dialogue between those groups either. Hence the kind of term, the echo chamber of Twitter. So that's one approach. And what you'll see, these community detection algorithms are probably going to be the most common approach to identifying groups within networks. Components, though, are very useful if you have smaller networks, just to get a sense of like what isolated groups within this network exist, especially like if you're studying classrooms or teachers or educators within a school district. It can be very enlightening and informing. In some cases, though, it just may be very obvious. You may see groups or components that emerge that are really based on physical characteristics of this school district or setting. So, for example, teachers interacting primarily with just teachers at their school, or superintendents interacting only with other central office administrators. So another way, and these are, honestly, I'm going to be totally honest, you probably won't see these types of approaches for identifying groups in the literature very often. They're very technical and mathematical, and honestly, not always the most useful way to identify groups. But similar to top-down methods, these approaches, these bottom-up approaches, are concerned with how larger structures are composed of smaller groups. But bottom-up approaches, they're basically built up from simple dyads and triads. So like which two people are connected together, which three people are connected together, which four people are connected together, and identifying groups that way. So one very common approach is you're going to have to stretch your brain just a little bit, but there's these things called K-cores, and K being any given integer from like 1 to 5 to 10 theoretically. But within this network, for example, we would say a one-core group are people who are connected to each other by at least one other person. So we can see 8 is connected to 7, 7 is connected to 3, and these people would constitute a group. Now, we could say within this group, they have to be connected to at least 2 other people who are connected to 2 other people. And in that case, this person number A, let's call it student number A, they would be excluded from this 2-core definition of a group because they're only connected to one other person in this group of people. And it goes on and on and on. So a 3-core group, that would limit and restrict our group to just those 3 individuals. This is a very simplistic way of describing a group. And I'm going to be honest, you probably won't see this very much in the literature. Any questions so far, though? I know I'm like introducing a lot, like very quickly, but I just want to give you like a sense of like when we're looking at groups within a network, like how we define those groups, how we say this is a group and this isn't a group. Cliques is another way. Basically, cliques is a way of saying it's kind of similar to cores, but it's saying like everybody that's a part of this group has to be connected. I'm trying to figure out, well, like, what is it? Hold on. An in-clique is maximally connected subgraph of nodes in which all other nodes are connected to each other. So which clique, I missed another typo. Which clique in the graph to the right? Which, oh gosh, I'm so sorry. I need to fix this slide. So this would be a one clique, I think. They're only connected to one other people. You know, I need to get out my Carolyn book because I'm actually personally struggling to figure out the difference between a core and a clique. Well, we clearly have some isolates. They're not connected to anybody. We clearly have people. These are connected to only one other group. And these people are connected to at least 2 other people in this group. Anyways, you can see some similarities between these two. And then there's a formal definition called a clan, and actors in the same clan, they're all connected at a certain distance between other actors in this network. So 2 clan, Oh, all of these people, I get it, forgive me. All these people in this clan over here, they're only 2 steps away from everybody else in this network. So you can see this person is only 2 steps away from that person. This person is not included in the clan because that person would actually be 3 degrees away from that person. But as you can see, like I said, you won't see these types of definitions of groups in the literature very often, but just so you know, they exist. Cores, cliques, and clans, and those are all bottom-up approaches. All right, so time for a little quick discussion. So think about a network that you're a part of, or you might be interested in studying, and consider the following questions. What groups might exist in this network? How might you go about identifying those groups in a way that might be meaningful to that context? And how do you think this information might be useful to you? And I'll give you like a few minutes to just think about this. And then I'll call on one of you randomly. Give you like 20 more seconds to think about it. All right, and I lied. I'm not going to put anybody on the spot and call on anybody randomly. Are there any volunteers that would like to just share out their responses or thoughts?
I was thinking, not one that I want to study, but in the community that I live in, we have people that are neighbors and live in close proximity and know each other. And then we also have a pool. So in the summer, you have people you see at the pool, and then there's also tennis. And so if someone plays tennis, like there's people that are like their cluster of like, oh, this is my tennis kind of crew. And then some people play golf. So then, some do all of it. And, you might know somebody from all of those, but then since I'm always just observing things at the pool in the summer, I like see the different clusters, and then some kids participate in the swim team. So then that's like another layer of some just go to the pool, but then if they're on swim team, some are swim together. And so there's like a lot of connection, but then also a lot of times you'll find someone that it's like, oh, I don't know that person. And it's like, how do you not know each other? But I suspect almost everyone is just one connection away from everybody.
That's a perfect example. What do you think might be some of the advantages of being a member of one of those groups, or even multiple groups, and disadvantages?
I think, if you, let's say you were like looking for a new job or something like that, somebody knows somebody who works at that place, if it's somewhere local. But then also everybody kind of knows, it's like, oh, well, they do this on Tuesdays or they're there. And so it's like you can't really go under the radar for stuff.
Perfect example. That was excellent. Thanks, Susan. All right. Okay. So here's what it looks like in real life. So we talked about it kind of theoretically and on paper. We actually did see some examples, concrete examples from real data for defining each of these things. But we're going to look at this one study really quick and use some data not from their study because they didn't make their data public, but we do have data from Twitter that I pulled myself that we'll be working with. But anyways, this study is really interesting. If you remember from the summer, you did my SNA labs, we probably came across it at least once. But this is a study by Alan Daly, who's a big network guy at University of San Diego, and some of his colleagues. And I think most of these folks are from California, but I could be wrong. But anyways, they did this like really long, intensive, in-depth study that resulted in this really cool website as a sort of data product for this. Instead of, they had traditional journal articles published from all of this, but honestly, the website is the coolest product out of all of their work. And it's called this #Common Core project. And what they did was examine this Twitter debate from a number of different angles, this Twitter debate over the Common Core state standards. And they did network analysis, they did a lot of text mining, they did some traditional qualitative analysis, and it was really interesting. But what they were really looking at for this particular aspect of it is like they were wondering how social media enabled social networks are changing the discourse in American politics that produce and sustain education policy. That's like a really, really broad question. Simpler questions that they were looking at, though, that are like very easy to understand, were like, who were some of the key individuals that emerged out of this big giant Twitter network? And these key individuals being those who tweeted about the Common Core a lot, or those who were actually more influential and were not only tweeting about it, but also being the recipient of tweets from a lot of people about the Common Core, maybe because people agreed with their thoughts, or maybe because they were saying something profound or important, or retweeted their thoughts too. And I think we maybe got into this during the summer, I can't remember, but we're working on this right now with my SNA class. To get this data, they use Twitter's API, which is basically a way of letting my computer talk to your computer to get data from your servers, in a very simple way. And in order to set up this Twitter API, my students right now, some of them, because it was optional, some of them has set up Twitter developer accounts. And once you set up a developer account with Twitter, you can then use their API. And if you set up an academic developer account, you can actually get full access to their entire Twitter archive. So you can go back like 10 years and pull millions of tweets around certain hashtags, or for certain individuals, or for certain keywords. And that's effectively what they did. And they pulled like tens of millions of tweets from tens of thousands of users and said, hey, what can we learn about this discussion about the Common Core from all of this data that's being spewed out of Twitter? And here were some of their key findings. And I sort of narrowed the key findings down to as they were specific and pertain to our discussion about groups and key actors in a network. But they've, I think, Melinda, you nailed it earlier in the beginning, was in their communities, these community detection algorithms that they were using to identify groups within a network, specifically kind of larger groups within a network. They identified like 5 major groups or factions within a network. It's going on pause because I think I have it set up on a timer to go on pause, so it doesn't charge me for when I'm not really using it. So sorry about that. Let me read that. And in the meantime, any questions or comments so far? But Melinda, like I said, you kind of nailed it. One was a big group, and these groups were like, you know, fairly connected to each other, either by like 1 or 2 or 3 degrees of separation. There's a bit more interactivity between members of this group. And one of them, it turns out, was like key supporters of the Common Core. One of the groups was key opponents inside education, so teachers and educators who did not like the Common Core. And then also opponents of the Common Core outside of education, which was really interesting. I found number 2 to be most interesting of all. And then another thing that they found was they noted that most of the participants in the discussion, like just like social media, were just like on the fringe. They're just casual engagers with Twitter, like maybe tweeted 1 or 2 tweets about the Common Core, and that was it. And then there were kind of 2 types of actors on Twitter. These transmitters, these are people who are, in network speak, we call this out degree, people who tweet to other people, regardless of whether or not they receive any replies and regardless of whether or not it's reciprocated, but people who tweet to other people about the Common Core. And, you know, within these tens of thousands of people, there's like a small handful of people who just either really hated it or really advocated for it and were very active on Twitter and tweeting to a lot of people about it. Some of them were probably, to be perfectly honest, bots. And I don't know if they ever got into that, identifying like which users were bots and which were real people. And then finally, these transceivers. These are people who are the people at who these tweets are directed. So members of education unions, for example, might receive a lot of tweets, or members of certain educational organizations or organizational accounts themselves that people are tweeting at. All right, so now we get into the hands-on portion. Does anybody need like a break really quick? Or have any questions or anything? And you guys are free to go at any time too. You can hang out as long as you want. We're going to work through some code and do some practicing with some real data. But if you have to go, I completely understand as well. And I do have to hop off at 11:30 today, so a little bit earlier, and cut into our open office hours because I have a meeting with our evaluator for the Laser Institute as well. And we're going to be talking about some data collection this fall and spring. All right, so if you want to follow along, I'm going to ask you now to go ahead and open up an R script, and we'll just work with a blank R script. We won't work with an R Markdown file. Does everybody remember the difference between an R script and an R Markdown file? Or anybody have any guesses?
So in the R script, don't you just have the normal like function or coding, where in the Markdown file you've put it into a format so that you can knit it?
Yeah. So an R script is just for code. It's a way to write your code and save it and run your code. And you can write like comments if you use a hashtag, like this code is for loading libraries. But you will never turn this into anything beyond what you see as just a very simple text document for writing code. Whereas an R Markdown file has code. See all this R code? This is R code, and it has like the actual code, but it also has text. And this text is translated into like normal text, like in a like PowerPoint presentation. Like these are bullets basically, or narrative, things like that. So it's a mix of code and text, R Markdown. And this mix of code and text can be translated and turned into slides. It can be turned into web pages. It can be actually turned into supervised machine learning text analysis in R. Supervise. This book, this online book, this whole book is actually a bunch of R Markdown documents that have been knitted and turned into an entire book. So R Markdown is super, super powerful. You can create books, you can create web pages, you can create blogs, a whole mess of things. And it looks like I somehow lost all of my other tabs. Not sure how that happened. Let's go back here. Apologies for that. Back to your contents. Right, let me reknit this. Then I got my R script. All right, so first thing we're going to do is load our libraries. So let's go ahead and do that. If you have the slide open, you can just go ahead and copy, and you can paste it in your R script. And we're going to load the tidyverse library, run code, and we're going to load the tidygraph library, which is for network analysis. The tidygraph, just to jog your memory, that is a way for creating network data graph objects that we can manipulate and visualize and do a whole host of things and calculate network metrics. And this GG graph package, actually it's G giraffe, like a giraffe. This package is just for network visualization, for creating really nice visualizations. I actually used this recently for some evaluation on work that I'm doing for this Network of Networks project. That is a bunch of agricultural networks at different institutes of higher education that are trying to work together and collaborate on projects. And I just used it to create some really nice visualizations for their annual report to NSF. And then the iGraph package is an old package for R for network analysis that's been around for a really long time, and is a little antiquated, but is also still super useful, especially useful for calculating network level metrics. All right, so we got those loaded. And if anybody needs me to slow down, just let me know. And now we're going to import our data files. So if you go to, we're in lab 3 right now. In lab 3, there's a data folder. And in this data folder, there's some data that we're going to be using for this, these Common Core state standard tweets. So what we're going to do is we're going to go ahead and import those into our environment. So we're going to use our, anybody know what this read CSV function does?
It reads in a CSV file.
Yeah, it reads in a CSV file. And the read CSV function is from a package called dplyr, and this dplyr package is a package that's loaded with the tidyverse. And when you run the tidyverse library, it loads for you like 12 different packages that are super useful. So it reads CSV files. And what, Melinda, what CSV file are we actually going to be reading in?
It looks like we are going to read in the edge list and the node list, and we're going to assign them to ties and nodes so that those are the data frame, right? That's
exactly right. Yep. We're going to take these CSV files and we're going to create a data frame, and we're going to name that data frame CCS ties and CCSS nodes. And once we've read them into R, then we can start doing stuff to them. And the thing I love about working with data in R is once we read these in, oh, you know what, forgive me. Does anybody know why it's not reading it in for me? Why I'm getting an error?
You don't have your working directory set properly.
It is set for, it's set actually for an R script, it's set at the project level. So when I say read the data folder, this is the beginning of my project, and you see a data folder here. There's no data folder. The data folder is actually in my lab 3 folder. So I need to say, hey, look in the lab 3 folder, then look in the data folder, and then look for a file called ccss-edgelist.csv. So let me do that, and then it's going to read it in. All right, so lab, and that's the difference actually, Melinda, between our script and our Markdown file. And our Markdown file actually is going to look in the folder that our Markdown file is in. So since this Markdown file is already in my lab 3 folder, it's going to look in here and not at the project level, not at the top level. And our script is only going to look at the very beginning of where your project directory starts. So now if I look in my environment, you'll know you did this correctly and it worked, because now we're going to see two data frames in here. Our nodes data frame, and I'm going to open that up. And these are all the users in this small Twitter network. I only pulled a small set of tweets for this. But even in the small network, you can see we have 92 users. And I think it's only for like 2 weeks worth of tweets. And then we're going to pull in all of our ties. So these 92 people generated, still going. These 92 people generated 289 tweets. So that's what, on average, about like 3 tweets a person maybe. And what we're going to see when we visualize this network is that most of these tweets are from from a few individuals. This RDS Athene, I don't know who it is. I think this might be a bot, to be honest. All right, so far so good for those that are following along. Any issues so far? Okay, so we got our data. And I'll be honest, the ties data, I didn't do a lot of cleaning for this. This is basically the way it's spit out of the Twitter API, which is nice. The only cleaning that I had to do was, it doesn't tell you nice and neatly who is responding to who, like who's sending their tweet to who else in the network. It's stored a little differently. So I did have to do some text pre-processing to get this ready. And we can see the content of their tweets as well. So it makes this type of data set makes for like a perfect context for network analysis and for text mining at the same time, which is exactly what the Common Core project did. So, oops, sorry. I'll go to their return to the Common Core projects. Loading. I'm impressed they have kept this website maintained as well, because I think they wrapped up this project in maybe 2018 or so. But you can see they looked at the network as a whole. They looked at key actors in the network. They looked at time periods when there was the most activity around the hashtag Common Core. And then they did some text analysis as well. And they looked at, again, most of these were very automated approaches, although they did do some hand qualitative analysis as well. But they looked at things like sentiment, like mood, positive, negative tweets. And if anybody did the text mining labs, there's different lexicons for sentiment analysis. Some are just binary, like positive or negative. Some are coded with things like anger or sadness, or basically words that are associated with those concepts. So anyways, oh yeah, and they also used another type of lexicon, I think it's called the linguistic inquiry word count lexicon, which is a way for measuring certain writing styles and writing attributes. So anyways, that's that. So far so good. Let's go back to our slides. So go ahead and take a look at this data. If you type view down here, you can do lowercase or uppercase views and the name of the object that you created, ties. It will actually go ahead and pop this up into your source pane. The fast way to do this though, Larissa, if you don't feel like writing the code for it, is if you just go over to your environment pane and click on the object that you want to see, it will just open it up for you. And you can actually see down here at the bottom where it runs the code for you. All right, so there we go. We'll skip this part. Quick question though, from the group. I'm going to open up my ties. And can someone tell me the difference between the sender and the receiver columns for this edge list? Like, what does sender signify and what does receiver signify?
I think the receiver is if they were added. I don't know
Yep.
the at thing.
Yep, the receiver is if someone like said, "Hey," at Susan, or "Hey," at Larissa. So it's someone sending a tweet to that person. And then the sender is the writer of the tweet, though. So the sender is the person who actually did the tweeting. And you can tell this is, forgive me, a directed network, because Banjo Tanjo might have did tweet to Millennial Other, but Millennial Other may have never responded or acknowledged that person's tweet. But if they did, if Millennial Other did tweet back to Banjo Tanjo, what would we call that type of tweet or that type of tie or relationship?
Reciprocal.
Yep, reciprocal. These handles are really interesting. Booker Spartacus, One Tough Nerd. And some of these actually seem like real names. John Rappaport. Anyways, so here is the most unique thing about network analysis. So when we are doing traditional data analysis, we're typically working with a single data frame, right? It might be a data frame that has students and all of their test scores and demographic information and a whole host of other things. And basically that's our data set that we're working with, right? But when we're working with network data, we often have to combine two data frames together into a single object, into a single type of network data structure. Because we have information about our ties, but we also have information about each of these individuals in this network. Now, this one is super simple. We only have the name of these individuals, but it could have additional information that's relevant to the type of analysis that we want to do. For example, it might be how many followers they have. So we get a sense of whether they're like influential on Twitter or like just a nobody on Twitter. It might have information about like when they joined Twitter. So are they a noob or have they been around Twitter for a long time? It might have information about gender. It even has information, if they share it, about where they're located and where they're from too. So that's why we often have two separate files that we have to merge into one file, because we have information about the individuals in our network. And we also have information about the relationships between these individuals. So it's not just whether or not there was a tie, but in our case for Twitter, like when that tweet happened. So we could actually, if we wanted to do some dynamic network analysis and show the network evolving over time and changing over time, and even create an animated network object in R if we wanted to. And it also has information about like what that tweet was about too. So what we're going to do next is we are going to do something that's very typical in network analysis, is we're going to create a new object. And this is not a data frame. It's not a rectangular data frame. It's combining two data frames into something unique, something that's different, and it's called a network object, or in our case, it's called a table, not a data table, but a table graph. And this table graph function is actually from the tidygraph package, and it's going to take our edges, and it's going to take our nodes, and it's going to combine them into a network object, and we're going to tell this function that this network is directed, meaning that I can tweet at you, but you may not tweet back, which has implications for our community detection algorithms, because some ways of detecting groups in a network, those algorithms only work on directed networks, or those algorithms only work on undirected networks. So we're going to say our network is directed. Here's our edges. Here's our nodes. Put it all together and make a network object. So let's go ahead and run that. And then we can see we have a new object up on our environment, and it's called CCSS network. And if you click on it, you're just going to see what looks like gibberish. Because again, a network object is not a traditional data frame. It's not like our nodes object or our ties object. So despite that, even though we can't click on this and see anything meaningful, what we can do to this is we can actually print this network object and take a look at it, and it will tell us information about this network. So go ahead and type in the name of the object and just run that code. Just take a look at the network object, and you're going to see it's going to give you information about your network. And really quick, Larissa, I'm going to pick on you if you don't mind. In this network object, we see we have 92 nodes and 289 edges. How many people are in our network? How many actors are in our network?
Uh, 92.
Yeah, there's 92 actors in our network. And there were 289 ties, or in this case, a tie is a tweet. And any volunteers to tell me what this means, that there's 13 components? And I'll give you a quick clue.
So groups.
Yeah, 13 groups. A group being, yeah, Sonia, you got it. A group being actors who are only connected to each other, but nobody else in the network. And actually, now that I remember, this is actually a very, very simple visualization of the Twitter network that we just created. There were 13 groups here. Oh, what's interesting is it looks different than the first time we saw it, because every time I knit, there's a little bit of randomness to the sociogram visualization. So every time you create a new sociogram, it's always going to look a little bit different. All right, so we have a network object, which is good. All right. And now we're going to take a look at a sociogram. Oops, sorry about that. So what's going on? You can go ahead and copy this code. I'll walk you through it in a little bit, but actually do this. For those of you that are actually typing things out in R, here's what I'd like you to do. There's a little function that's super useful called autograph. And the autograph function is from the gggraph package, and it will create a network visualization for you, a super simple one that requires like virtually no code at all. And if you go ahead and run that, see what happens and tell me what you get.
Basically that slide again, only mine is like in a line.
Yeah, the autograph function will it will lay out each component right next to each other. That's what the autograph function does, and it creates a very simple network visualization. So here's one component, and if you notice, it actually lays out the components based on their size. So these are the smallest components, and then groups of 3, and then a group of 3 that's interconnected, and then a group of 5, and then another group of 5, and then a group of whatever that is, 7, 8, and then the larger component too. And there's one more function that's fun to play with. This is built into R, and plot works with a whole mess of things, but it even works with network objects. So type plot, the plot function, and feed it your network object and see what it creates. What'd you get, Larissa?
Yeah, beautiful. So I can see the numbers.
Yeah, the plot function is nice. It provides labels. It also shows directionality. If you actually, you can make this, here, let's see if I can zoom in. I don't know if you can see that pop-out window, but you can make the window even bigger. The plot function, to be perfectly honest, it works really well with very small networks. But once you get beyond like maybe 20 people, it's just kind of a mess. So what I've done is I put together some code for you from the gggraph package, and it works just like the ggplot package. So we have a central, the case study walks through all of this if you want to like see how these are all put together and like what each of these functions mean and how we build a graph layer by layer. But this function right here says, hey, this is my network, and this is the algorithm I'm going to use to lay out my graph. This FR algorithm is probably one of the most common algorithms for laying out graphs. And I'm going to say to my graph, I want you to add the lines, the links between people. And I also want you to add the actors to my network and make them a point on the graph, but they don't have to be points. They could be like other things too. They could just be labels. We could just have the labels with like no circles. And I'm also saying, hey, you know what? I want you to add the labels too. So let's add the labels for them. And then I want you to, this is like a shortcut for making your graph pretty. You can apply themes to your graphs too, and it will like lay out your graph and like remove clutter and make it pretty too. So this isn't going to be super pretty, but if you run that, you're going to get something that looks kind of like that. So it's a little bit more clear than the plot function, and we can see each of our components still. So there's all of our components. Each component has a label, has their name. We can also see the directionality of the arrows. And then we can see kind of our core network. But our core network, is it centralized or is it decentralized?
I would
It's
say
pretty-
it's centralized.
Very centralized around this one individual. In fact, I said in my graph here, the point, I said, change the size of my point to be based on how many people they're connected to. So the more people they're connected to, the bigger to make it. So it looks like 50 is kind of our upper limit for how many people a person is connected to. And this person is basically, if you look at the arrows, they're all pointing outwards. And this is someone who's just tweeting at a whole bunch of people. All right. So now we're going to do some components. Oh, I went ahead of myself. Sorry. The autograph, actually, I got ahead of myself. The autograph function will lay out your graph and show you each of the components right next to each other, which you just saw. I'll show that one more time. And it arranges the components by size too. And if you remember, if we go back up here, we can see that our graph has 13 components. And there's each of the components. And remember, component is like the simplest definition in network analysis of a group. But also the components can be meaningful in and of themselves to see where people within this larger network, where they're isolated amongst each other. And Melinda, I was saying earlier, we can look at components and we can look at, see whether those components are reciprocated or not reciprocated. And we can say, hey, we want to look at components, but only those components where everybody's connected to each other in a reciprocated way. So I'm going to run this and we're going to take a look at this and see what happens. So let me run my script again. And I'm going to copy this onto my R script, and I'm going to run this component analysis. And so now we can see that we had 13 components before, and now we have 92 separate components. So if we only look at the reciprocated ties, then we're going to see that these people who seem to be really well connected, once we look at these people, once we look at these people, but only look at reciprocated ties between these people, they break apart. So these connections between these components, these groups, they're not very strong. They're all probably mostly just one-way connections. And I'm sorry, this components function comes from that old iGraph package. Hence, this kind of primitive R output that you'll see, and that's why it looks kind of old. And it's basically assigning each of the members, these 92 actors in their network, it's assigning each of them to a group. And actor number 1 is a member of group 91, group 92, group 86. And you can see most of these people actually, oh, that's really interesting. Okay, so we actually have 92 groups basically. So there's no groups that are intricately that are connected in a reciprocated way. That's kind of interesting. All right, and we're almost done. Sorry about that. And again, if you need to hop on, like I will not be offended at all. Clicks are another way that we've talked about. There is a way to run a function where we can say, hey, just tell me how many clicks are in this. And, oh, did I get an output for that? We'll do edge direction ignored. Oh, sorry. Basically, if we look at how many clicks there are in this network, so people who are connected to each other by at least like 3 connections, we only have like 3 clicks or something. I'm kind of curious. Anyways, like I said, you'll see clicks a little bit more frequently than things like cores or clans, but it's not a definition of a group that's used very frequently. All right, key actors. We're running short on time. I'm going to run through this really quick. This is actually probably the most useful information. What we can do within this network is, let me go back to my source, my R script, is we can, just like when we're using tidyverse packages, we can say, hey, I want to take my network and I'm going to run this function. It's very important. It's called activating nodes. So it's saying, hey, all of the nodes in my network, the actors in my network, I'm going to create some measures for the actors in those networks. And I'm going to create some measures of centrality. So I'm going to create this new measure for each actor in my network. And this measure is a degree measure of centrality. And it's basically how many tweets are coming into you. How many times have you been tweeted at? And this out one is how many times have you tweeted at other people? And these will be measures for these individuals that are then going to be added to our network objects. So let me run this and I'll show you what I'm talking about. So I'm going to run that. And again, I'm going through everything really fast, but it's all explained in the case study as well. So it's all described in much more detail. So now let's take a look at this. I'm going to show you basically what this does. So I run this. And now remember, before we had just the name of the people in this network, but we didn't have any other information about these individuals. Now we have information about these individuals. This Alexios as text, he has nobody tweeted at him. He has 0 incoming ties to him. And he tweeted at one other person, or he only did one tweet to another individual just once. This Texas Granny has no ties coming in. Nobody's paying any attention to her. Nobody's tweeting at her, but she tweeted at people 4 times. And this is just like one measure that we can add to our node list. I want to show you something really quick though. It doesn't add it to your original object. So here's our original node list. It's only adding it to this network object that we created. But if you want to, you can export this node list with all of the actors and all of their measures, their network measures, and you can export it as a CSV file and use it as just a typical data frame. And then you might incorporate it into some other type of analysis where you might be asking, like, is someone who has a higher N degree within this network more likely to feel a sense of belonging to the network? And you might capture that information through like a survey or through some other means. Or are students in a classroom who are more connected to other individuals in the classroom, do those students have higher grades? and you might incorporate those measures into a more traditional standard analysis. And you can export this node list as like a CSV file. And that's it. All right, I'm sorry we ran over by 17 minutes. We still have 13 minutes if we want to hang on, if you guys have questions or if there's anything I can help with as well. And I'm going to stop the recording too. And stopping the recording.